So, all right. So this is actually a pretty cool section. I just skimmed through it, and we're gonna do the problems, but I am gonna walk through the notes of it too. Okay. So the idea is this whole chapter is about generalizing the past 3 chapters, which have all been studies of Rn basically, and generalizing it to the abstract definition of vector space that we just went over. So here's a little reminder of what null space is. It's basically all the x such that ax equals 0. And we can do this of a matrix, but this is the general and okay, here's the definition of null space. I feel like we've seen this exact definition before. I don't really know why they're saying it again, but that's fine. Okay, here. So verify if U is in the null space. This is really easy. It's easy to, we'll see this table coming up later. That's really cool. Anyway, so A times U, if you just do this matrix vector multiplication and you get 0, 0, then U is in the null space. So thus U is in the null space. Okay, the term space in null space is appropriate because null space of a matrix actually is a vector space. Okay, and that's an important theorem. The null space of an n by n matrix A is the subspace of Rn. So if you're thinking about, we have m equations and n unknowns. Then when you're thinking about the set of x such that ax equal to 0, as is such in the definition of a null space, then it's going to be a subset of the vectors in Rn, not Rm. So you just need to make sure that you understand which side you're on, basically. So anyways, the set of all solutions x such that ax is equal to 0 of m homogeneous linear equations in n unknowns is a subspace of Rn. Okay, so the proof is, first off, obviously it's a, okay. All right, so 0 is in the null space because, you know, A times 0 is going to be equal to 0. We've shown that in chapter 2 with matrix algebra. Okay, then let them be 2 solutions. So then we're going to try to find whether or not. So, okay, so wait, let's just spell out what's happening here. So U is an element of the null space and V is an element of the null space. So now we need to make sure that A times U plus V is in the null space. So i.e. A times U plus V is equal to 0. And we can just distribute this out. And so we can then show that that the null space is closed under addition. Now we want to show that you can scale it. And this is just that classic thing that you it's basically by the definition of A being a linear transformation, these 2 things are equivalent. So then once you move the scalar outside of the equation, then you can replace AU with 0 because we assumed that that U is an element of the null space. So then we're going to get C times 0. All right, great. Another example. Let H be the set of all vectors in R4 whose coordinates A, B, C, D satisfy the following equations. Show that H is a subspace. Okay, so this is another just like play around with the symbols type of thing. You just turn it into a homogeneous system. Okay, and since it is a homogeneous system, then wait, hold on. Show that H, where H is, okay, so H is all vectors in R4. That's how, so H is the null space. Okay, great. An explicit description. Okay, this is going back to this parametric thing. So you take you're trying to find a spanning set of vectors, so a basis for the null space. And you take some matrix, then you reduce it to reduced row echelon form, so you get this. Then you take the free variables and you write the non-free variables in terms of the free variables. And so then you get these column vectors in terms of your free variables. These form a spanning set of the null space. Oh, and there were a couple of good points in here. Okay, wait. The spanning set produced by the method in example 3 is automatically linearly independent because the free variables are the weights on the spanning vectors. Look at the second. Oh yeah, you're right. So the point is that if you look at this, and this, the only way that you could ever make, W plus U, or a linear combination of U, V, and W equal to 0 is if they were all 0. So just goes to show that just the way that we do this process always generates a linearly independent set. And then the second point was when the null space contains non-zero vectors, the number of vectors in the spanning set of the null space equals the number of free variables in the equation. Okay, yeah. This goes back to the dimension thing, but they're not really talking about dimension right now because they're trying to get us. I mean, because dimension, I don't know is, it's been a while since I've done linear algebra, so I don't remember exactly how dimension is for more abstract vector spaces that aren't just Rn and Rm and stuff and whatever. Okay, all right. So they remind us of the definition of the column space. It's just basically the column space is the span of the columns of A. Oh yeah, and then here this is sort of the other way around. When we were talking about the null space is a subspace of Rn, but the column space is a subset of Rm because it's a linear combination of the n column vectors who each have m entries. So when you take a linear combination of the columns, you're going to end up with a vector in Rm. Therefore, the column space is a subspace of Rm. Okay, that one's easy. Here's the definition written in a different way as the span, but it's the set of B such that B is equal to AX for some AX or for some X in Rn. That one's easy. Find a matrix A such that W is equal to the column space of A. Okay, this one's a good problem because so we have 3 equations and 2 unknowns. So we can end up rewriting this by splitting out the A's and the B's like this, and then we find our spanning set. Great. The column space of n matrix. Right. This is just reminding us that, if the column space of your matrix spans Rm, then it must be that each B in Rm has a unique solution for X. So it's onto Rm. Okay, row space. The row space is just like the column space, except for the rows. It's the span of the rows of A. Similarly, the span of the columns of A transpose, obviously. The contrast between the null space and the column space. All right, yeah, we'll work through this one. Okay, so let A be this. If the column space of A is a subspace of Rk, what is K? So the column space is going to be a subspace of R3. And the null space is going to be a subset of R4 because it's the vectors A times X such that equal to 0. So X has to be in R4. And then for some vector X, AX equal to B, B is going to be in R3. Okay, so K equals 3, K equals 4, like we said. What's this one? Find a non-zero vector in the column space. So that one's easy because it's easy to find a vector in the column space because you can always just take one of the columns of A itself. Now, finding a non-zero vector in the null space is a little bit harder because you need to row reduce it. So you need to do this, and then you do that spanning set thing, and then you pick a value for the free variables, and then when you do the linear combination, you're going to get a vector in the null space such that AX equals 0. determine if U is in the null of A. So but determining if a vector is in the null space is easy because all you have to do is do the matrix vector multiplication and check if the vector is the 0 vector. Finding if something is in the column space, however, is harder because you need to row reduce and see if it's consistent. You know, the augmented matrix AU is consistent, or AB, or whatever variable name you want to call it. So anyways, so for A, they did A times U, and they found that it wasn't the 0 vector, so therefore it's not in the null space. And then to find whether or not V is in the column space, they put it into echelon form, and they find that the equation is consistent. So since it's consistent, it has it's in the column space. It's a little bit interesting, though. Okay, yeah, all right, that's fine. Okay, this table is what I was talking about. Okay, so the contrast between the null space and the column space. The null space is a subspace of Rn. Okay, this is all for an m by n. Okay, the only thing I really wanted to go over here, you can pause and read this, and I suggest you read it because then you actually take a second to think about it. But the point was, you know, the null space is it takes time to find vectors in the null space, but it is easy to tell if a vector is in the null space. And then it's sort of the other way around. It's easy to find vectors in the column space, but it takes time to figure out if a vector is in the column space. So kind of the duality of the null space and the column space. It's really cool, actually. All right, then they come back to the definition of a linear transformation. Okay, and then they're bringing up new terminology. So they're saying the null space is no longer just defined on matrices, but we're now talking about the set of all U such that TU is equal to 0. So this is for arbitrary vector spaces V and W and linear transformation from V to W. Okay. Okay. Oh, and then they define the range as kind of the linear transformation analog to the column space. It's the set of all vectors in W of the form T of X for some X in V. So we've introduced kernel and range as sort of the generalizations of null space and column space for matrices or matrix transformations. All right, so here's some cool examples. Okay, so this one's really cool, and I think we've actually done this recently, but you basically show that that the derivative operator or the differentiation operator is a linear transformation from the space of functions that are differentiable and have continuous derivatives, and the space of all continuous functions on AB, or on the closed interval AB. And then this one's really cool. This shows that the solution space of the harmonic oscillator the set of solutions of the harmonic oscillator is precisely the kernel of the linear transformation that maps a function y equal to f of t into the function f double prime plus omega squared f of t. Right, so if that's 0, then it's in the kernel. And finding an explicit description of this vector space And we went over that problem. We went over this problem with the C1 times cos omega t plus C2 times sine omega t or something like that. Okay, then they come over this example trying to analyze stock market data and create a moving average, and they're trying to show that the moving average of the past 2 days is a linear transformation, and they do the basic stuff of proving that that the transformation on two different signals is equal to the transformation on the individual signals applied to and then scaling a signal is the same as scaling the transformation of the signal. Or yeah, whatever. You guys get what I'm saying. This one's easy. All right, now we get to the problems. These problems are actually good. All right. Whew. Blowing through these sections, man. Okay, so W is equal to A, B, C, such that A minus 3B minus C is equal to 0. Okay, so what we can do is we can put this in that classic parametric vector form. So we have A is equal to 3B plus C, right? Now the point here is we can write this as B times 310 plus C times 101. So I'll do it over here. So for this, we're going to show in two different ways that W is a subspace. So the first theorem is we're going to show that there are vectors that we can write it as a linear combination. Okay, it's B times 310. Okay, so 310 plus C times 101. Okay, so this is the and C is okay. So we've expanded this out. So now we can write A as 3 1 1 0. Oh wait, what am I doing? Yeah, 3 1 1 0 0 1. Okay, so anyways, we found this matrix, and we found the linear combination. So this is going to be, this is W, and W is a subspace because it's all linear combinations of this form. I don't know what the second theorem is. Let's do the other two, and then we'll go check the answers. Okay, so let A be this matrix, V be this matrix, and W. Suppose that you know that AX equal to V and AX equal to W are both consistent. That means that there's some X1 equal, so there's AX1 is equal to V. AX2 is equal to W. So that means they're consistent because there exist X1 and X2. What can you say about the equation AX3 is equal to V plus W? So AX3, okay, the point is that we know it's consistent because AX1 plus AX2 is equal to V plus W. Now that doesn't immediately tell us that it's consistent, but what we need to do is we need to take the A out and make it X1 plus X2. Now we know that X1 plus X2 is going to be the element of the domain that we need. Okay, good. So it's to make this consistent. So this is just going to be A times parentheses X1 plus X2. All right. Let A be an N. Oh, this one's really good. I like this one. This one took me a little bit to figure out. I cheated a little bit. I looked at the answer. Okay, so let A be an n by n matrix. If the column space is equal to the null space, show that the null space of A squared is equal to Rn. Okay, this one's really cool. So first off, okay, let's let B be an element in the call space. Okay, what that means is that there exists some x such that AX is equal to B. Okay, but since call A is equal to null A, then what that means is that B is in the null space. Okay, and what that means is that if we applied A to B, we would get 0. But what B is AX. So if we did A times X is equal to 0. But then we can turn this into a matrix power, so we get A squared X is equal to 0. And since we took B as an arbitrary element of the column space, I don't think I'm finished though, because oh yeah, because for all x in, so A is n by n, so x is some, so let x in Rn, then A times x equals B. B is in Rn. By definition, it's in the okay, yeah. So you just pick an arbitrary element x in the domain. Then you know that the A times x that you picked is in the column space. But since the column space is equal to the null space, if you apply A again to that value, you're going to get 0. Therefore, for whatever value of x you pick, you're going to be eventually sent to, on 2 applications of the transformation, to 0. So the null space of A squared is Rn. That one's really good. I really like that one. Okay, let's see how they did this one. Yeah, so they did the exact same thing we did. And then, oh, they just used the definition of the fact that the column space is a vector space, and so it's closed under addition. They didn't even do the whole thing that I did. This is a better answer than me. All right, let x be any vector. Okay, so this is how I eventually got there, but I sort of did it a roundabout way. Notice AX is in the column space since it's a linear combination of the columns. But since call A is equal to null A, then the vector AX is also in the null space. So what that means by definition is that A squared X is equal to AAX equal to 0. Nice. I like that last one. Okay, so I think we're gonna breeze through these. There was a few that were really good, and then a lot of them that were just kind of silly. Determine if W is in the null space. Do the matrix vector multiplication. Do the matrix vector multiplication. We don't need to do these. All right, find an explicit description of the null space. We'll just do one of them. We'll do this one. All right, so what we're gonna do, okay, then, okay, so does this not work? It promotes it, dude. I wish it wouldn't promote it. Okay, so which problem is this? 6. Okay, so we're gonna have x1 plus 6x3 minus 8x4 plus x5 is equal to 0. And we're going to have x2 minus 2x3 plus x4 is equal to 0. So now if we turn this into x1 equals minus 6x3 plus 8x4 minus x5, and x2 is equal to 2x3 minus x4, then we know that x3, x4, and x5 are free. So we should be able to write this as x3 times minus 6, 2, 1. Wait, actually, hold on. I'm confused. Oh, wait, hold on. So we're trying to find an explicit basis of the null space. We're trying to find a spanning set of the null space. Find an explicit description of null A by listing vectors that span the null space. So since null of A is contained in Rn, which is equal to R5. Okay, good. Yes. So there's no confusion here. So then, so we got that plus x4 times 8 minus 1, 0, 1, 0 plus x5 times minus 1, 0, 0, 0, 1. Okay, so I got all right, so this is the form that I got. So then what this means is that for any assignment of x3, x4, and x5, we will get an element of the null space. So we have this original A matrix, right? So what we're going to do is, I think I can say substitute x1 to 1, x2 to 1, x3 to 1. Can I do this? Bro. Dude, it's actually so hilarious how bad their symbolic manipulation is. Wait, what? This didn't even work. Oh my god. What a joke. I think I can do this. Oh, wait. But what I wanted to do was, okay, I understand. This needs to be x3, x4, x5. Okay, so you just have to turn it to a dict. Okay, so wow, that's pretty coincidental, I feel like. Okay, so now if I do A times this, we're going to get... Okay, so this is... All right, so we did it. We did it. Took us a little bit, but we did it. Why are you watching them? All right. I don't know. Okay. Use an appropriate theorem to show that the given set W is a vector space, or find a specific example to the contrary. All right. I wanted to do these because I feel like these are pretty good. All right. So 7, W is the set A, B, C, such that A plus B plus C is equal to 2. So the thing about this one is, if you... The zero element... The zero vector is not in W. So 0 is not in W. Therefore, not a vector space. Okay. RST. Okay, hold on. This one's RST such that 5R minus 1 is equal to S plus 2T. All right, so if we rewrite this as 5R minus S minus 2T is equal to 1. Again, I think it's just because 0 is not an element of W. This one might be all right, so let's do number 9. Okay. A minus 2B to the 4C. All right, so wait, so what we're going to do, okay, yeah, this is exactly like what we had in the example. So we're going to rewrite these as two homogeneous equations in R4. So since we can write this as a homogeneous set of equations, I already know that this is going to be a subspace. But let's rewrite it out maybe. So you're going to get A minus 2B minus 4C is equal to 0. And then 2A minus C minus 3D is equal to 0. So then you get the matrix 1 minus 2 minus 4, 0, 2, 0, minus 1, minus 3. All right, so clearly, since you can write it as a matrix, it is a vector space. This one's also a vector space. 5 plus 2. Okay, so this one's interesting. So we skipped 10 because 10 was obvious, but 11 is not obvious. You have B minus 2D, 5 plus D, B plus 3D, and D, where B and D are real. We can rewrite this into our parametric form as we have that offset vector of 0, 5, 0, 0 plus B times 1, 0. Wait, actually, hold on. Yeah, 1, 0, 1. What were we saying earlier about right, okay. Okay, so let me just do it the slow way. So if we let d equal -5, then, because we're trying to find if 0 is in, we're testing if 0 is an element of the vector space. So d equal to -5. Then we're going to get b -10, b -15, and okay, so 0 is not in W. But if it was, then you'd have to do more work. Okay, so 11 is not a vector space. Because there's no way to satisfy that there's a 0 element. And all vector spaces need a 0. Similarly here, if D is 1/2, yeah, this is not a vector space. So 12 is no. And 13 is a vector space. And 14 is a vector space. All right, let's check our answers. All right, so wait, let me just double check what I got. I got no. Here, let me just do this. 7, no. 8, no. 9, yes. 10, yes. 11, no. 12, no. 13, yes. 14, yes. Okay. All right, let me keep reading. These are fun. These are pretty fun. So basically find A such that the given set is the column space. So yeah, you put it into that parametric vector form that we just have been doing, and then you take those column vectors and you just stick them into a matrix. Okay, so wait, what do we get? No, no, yes. Yes. No. No. Yes. Yes. All right, cool. So we got all those right. All right, do we even want to do this? I'll do one of them. So for 15, you get so there's 3 free variables. So we're going to write it as r times a vector 0, 1, 4, 3 plus s times 2, 1, 1, minus 1. And then what is the last t? Plus t times 3 minus 2, 0 minus 1. 3 minus 2, 0 minus 1. Okay, so then the column vectors I just said, you just stick those into a matrix. That's pretty easy. Okay, these are going to be pretty easy too. Find K such that the null space is a subspace of Rk. Okay, so this is a 3 by 2, so K is 2. So let's just write it down. So A, K equals 2. B, for the column space is going to be a subset of R3. So K equal to 3. All right, problem 18. This is just going to be, so it's a 3 by 4, so K equals 4 for the null space, and for the column space, K equals 3. For 19, And we get the idea, right? It's pretty simple. All right, so find a non-zero. This is just solving systems. We've solved so many systems at this point. This 23 I wanted to do. 23 was pretty good because, okay, observe that. So first off, determine if W is in the column space. So we need to find an X such that AX equal to W. So wait, we'll do it like this. So what was A? A was minus 6, 12, minus 6, 12, minus 3, 6. One thing to note is that this is clearly a linearly dependent set. So let's do A is equal to minus 6, 12, minus 3, 6. And then B, what is B? W is 2 and 1. So we're going to solve 2, 1. Oh, so it is not in the column space. Wait, but that doesn't check out for me. That doesn't make any sense, because if we're... All right, if we just write it as like x1 times minus 6 minus 3 plus x2 times 12, 6. I don't think that's right, man. Because what if you do A times 0, 1, 6? Yeah, what? How is that? That doesn't make any sense. A is like definitely in... All right, wait, if you... So this is x1 is equal to 2x2. So you take x1 equal to 2. Wait, what? I think it is in the column space. And then the interesting thing is... Okay, let's check if it's in the null space. It is in the null space, so yes, in null. But what about... I think it's in the column space. I think what happened is that the fact that it's linearly dependent caused this backslash to do something weird. What's up, Diego? No, I'm taking a class. And I agree with you. I think it's the best way to record your progress. Wait, but I wanted to know. Right. So okay. So actually, this. Okay. So why did Julia throw a singular exception when doing a backslash W? I mean, I know that the set is linearly dependent, the columns. It says on my machine. That's so goofy, man. That's actually really funny. Oh man, that's funny. On my machine. That's really weird. Okay, anyway, so yeah, so it's in both. That's what's cool, is that it yes in column 2. All right. We're not gonna do 24. Okay, the true falses are always some of the best problems in the book for sure. Okay, let's do, so the null space of A is the solution set AX equal to 0. That's true. 26. A null space is a vector space? True. 27. The null space of an m by n matrix is in Rm. That's false because the null space is a subset of Rn. So that's false. 28. The column space of an m by n matrix is in Rm. That is true. The column space of A is the range of the mapping A to AX. That's true, yeah. Call A is the set of all solutions of AX equal to B. That's false. Because it's not elements of the domain, it's elements of the range. So that's false. 31. If the equation AX equal to B is consistent, then call A is equal to... So they didn't say... This is one of those ones that's slightly ambiguous because... so then call A is equal to Rm. So if they said for all B, then I would say true. But since they didn't say for all B, I'm going to say false. Okay, 32. The null space of A is the kernel of the mapping. That's true. 33. The kernel of a linear transformation is a vector space. That's true. The range of a linear transformation is a vector space. True. Okay, what is it? Call A is the set of all vectors that can be written AX for some X. That's true. Um, 36. The set of all solutions of a homogeneous linear differential equation is the kernel of a linear transformation. That's true, but it's like, why are you even asking me that one? 37. The row space, it's like this, whatever. The row space of A is the same as the column space of A transpose. That's true. 38. The null space of A is the same as the row space of A transpose. False. All right, cool. Let me just double check all of the answers. Dude, I swear it's so much easier to learn now that we have ChatGPT. It's like, man, imagine not being able to check your work for every single problem. I love checking my work. Because there have been a number of times where I've been like, oh, I know it, but then I do it and it's not. Okay. True, false. Wait, 28, true, 29, true, 30, false, 31, false, 32, true, 33, true, 34, true, 35, true, 36, true, 37, true, 38, false. Nice. Easy. It can be shown that a solution of the system... Hold on, I'm going to get some water. Okay. It can be shown that a solution of the system x1 equal to 3. Okay, use this fact in the theory from this section to explain why another solution... Okay, so notice that this second solution is a scalar multiple of this first solution. So by the definition of linear... Well, hold on. So we have this homogeneous set of equations. If we have one solution, then we know that we can scale that solution and we'll still get another solution. Because the null space forms is a subspace and therefore is closed under scalar multiplication. 40, again, this is the exact same thing. Except in this case, it's that we have an element of the column space and so therefore we can scale an element of the column space and we know that that it's closed under that. So let me just try to write that out. So yeah, so you can just scale your prove theorem 3 as follows. Given an m by n matrix A, an element of the column space has the form AX for some x in Rn. Let AX and AW represent any two vectors in the column space. Explain why the zero vector is in the column space. I mean, I would just say because we know the column space is a vector space, so it has to have the zero. But also because A times 0 for any A is equal to 0, so then we just let X be 0, and therefore it's in the column. Then the zero vector is in the column space. Show that the vector AX plus AW is in the column space. Okay, so what that means is that I mean, part of me just wants to say you factor out the A, so then you find out that X plus W is going to be sent to... Or, oh, no, you know what you're supposed to do? I understand what you're supposed to do. So these are both elements. AX and AW are both elements of the column space. Therefore, since the column space is closed under addition, this is also in the column space. That is what you're supposed to say. Given a scalar C, show that... Okay, so this is the exact same thing. By the definition of the column space being a vector space, it's closed under scalar multiplication. Okay, these are the ones that I've been dying to do, bro. I've been rushing through just to get to these. When you talked about bend, oh, that's so cool, man. Yeah, dude, I've actually been... So I'm in classes right now, but I am dying to get back to... So I've been reading a ton about lambda calculus, and I've been working through some books, and I really want to get back to lambda calculus type systems and also graph rewriting systems. Hopefully in the late summer I'll have a ton of time to... Because there's this one book, Type Theory and Formal Proof, and I really want to work through this book. Anyways, we gotta keep on the grind, because for the next week I'm gonna be hitting the books. Okay, this one's really cool. Okay, so define a linear transformation from the polynomials of degree 2 at most 2 to R2 by T of P. Okay, so it takes a polynomial and returns the values polynomial at 0 and at 1. Show that it's a linear transformation. Okay. So let's say P of t is equal to A plus B times T plus C times... Yeah, I love that you can just use spaces. That's really nice. Okay, then oh wait, but this is supposed to be... What? Why isn't it letting me copy it? It's frozen. Dude, Firefox is so bad. What the hell? It was like Desmos earlier. Whatever. I don't really care. I'm just gonna do it on paper. So we're gonna have two polynomials, P of t and Q of t, and we're just gonna make them as abstract as possible. So P of t is equal to A plus BT plus CT squared. Q of t, on the other hand, is D plus ET plus FT squared. And now we want to know that show that t, where t takes p and sends it to p of 0 and p of 1 is linear. So we need to show that t of a p plus b, or let's just call it c1p and c2 q, is equal to c1 times t of p plus c2 of t of q. So basically we're applying the definition of linear. And so when we add these two, p plus q is equal to a plus d plus b plus e times t plus c times f of t squared. Okay? And wait, hold on. Okay, so t of this, so t of p plus q is equal to a plus d and a plus d plus b plus e plus c plus f. And if you do them separately as a and then a plus b plus c plus d plus d plus e plus f, so they're the same. So these two are the same. So, and then if you scale this, you're going to get, let's call the variable alpha or something. So we have like alpha a plus alpha bt plus alpha ct squared. So you can factor this. So then okay, so yeah, I think find, okay. So I think we did show that it is a linear transformation. Find a polynomial p in p2 that spans the kernel of t. That's a good problem. So for B, we're trying to find the U such that T times, or let's call it the polynomials such that the mapping to this is equal to the zero vector. So all right, so dude, yeah, Mathematica is so fucking good, man. If people don't, I swear, like, I know that a lot of people do know, but a ton of people that say they're programmers, they just don't know how goated Mathematica is. Like, it really is. I mean, if you know me from pattern rewriting, I wrote my own programming language that's almost identical to Mathematica just because I'm so obsessed with how cool it is. Pattern rewriting is just the fucking, oh man, it's just so good. Okay, so what is the kernel? The kernel is going to be all the polynomials that always get sent to zero. Maybe it's like, oh, it could be like um at minus at squared. Because then if you scale this, okay, my guess is that it's this. Okay, so now I want to see how ChatGPT answers. Because oh, and describe the range of t. So I don't know how to show that it spans the kernel though. Because really, I just found a family. Oh, you know what you can do? I think you can do something like, um, 1 minus 1. So this is going to be a times 1 minus 1, 0, plus b times 1, 0 minus 1, plus c 1, 0 minus 0, 1 minus 1. I think that that might be the span of the thing. So for the if you write it as like a times 1 minus 1, 0 plus b times 1, 0 minus 1 plus c times 1 minus, this is minus 1. Then if this is the case, wait, this is not true though. This is not right. No, that's not going to work at all. Wait, is it? Let's take 1, 1, 1. Let's just see. So you're going to get 2. I think this might be so what I'm saying is that this is a basis for the coefficients such that it spans the kernel. But I want to see what the real answer is. But I'm pretty sure that that's right. And then describe the range. I think the range. Is there any reason why the range can't be just R2? I actually have no idea. I don't think the range is R2. Maybe it is, though. Damn, I can't tell. Okay, so this is the standard. Just show it's linear. You show that you can distribute out the transformation over a sum, and then you can scale the transformation. Okay. T squared minus t. Okay, so oh. Oh yeah, that doesn't work. P of 0 not equal to 0. Yeah, so it does. It has to be okay. So my original thing of t minus at squared is correct. Um, okay, yeah. So this is so it's t minus or t squared minus t. That's the answer. And then what does it say for describing the range? Okay, so it is R2. Yeah. Okay, so I didn't actually write all that out, but range of t is equal to R2 because take AB in R2 and let P of t equal B minus A times t plus A. Wow, that's wild. Wow, that's so smart. You just draw a line between the 2 points. That's crazy. Wow. I haven't seen a rank nullity argument in a more abstract vector space like the polynomials. Let's see. I wanted to do these. I think I wanted to do this one too. So if T of P is equal to P of 0, P of 0. I think then the curve is spanned by AT plus BT squared, right? You just need the offset to be 0. And then the range, is just a line, right? But I think it's just a line, right? Because it's gonna be equal. So okay, cool. This is exactly what I wrote down. I don't really understand. Nice. Okay, that's what I got. One-dimensional diagonal subspace. That's a good problem. I really like this one, 44. 43 and 44. Because they're starting to get you out of your mind of just thinking about the boring vector spaces kind of. Okay, to show it's a linear transformation. Okay, so 45, T of A is equal to A plus A transpose for A in M 2 by 2. Then to show that T, so then A, show T is linear. So to show T is linear, we need to T A plus B is equal to T of A plus T of B. So we're going to get, so T of A plus B, we're going to get A plus B plus A plus B transpose. So, okay, wait, let me write it down so that we can see it. So T of A is equal to A plus transpose A. Okay? I don't know if I should have done that. Okay, but then if we do T of A plus B is going to be equal to T of, this is going to be equal to A plus B plus A plus B transpose. Okay. Wait, what? It said the identity though? Wait, what? For number types, adjoint returns the complex conjugate, and therefore it is equivalent to the identity function for real numbers. Oh, wait. Oh. Okay, for real matrices, the adjoint is okay. So I can write this. Okay, now the question is, we're gonna get T of A plus T of B. Okay, so if we just expand that definition, we're gonna get A plus A transpose plus B transpose. I don't know how to show that these are equivalent because, oh wait, but there's an identity actually. I think let me go back to matrix algebra. Maybe it's in here. Oh, okay, here we go. I think if you have A plus B all transposed is equal to A transpose plus B transpose. Because why wouldn't it be, right? Like if you have A, B, C, D plus E, F, G, H, and then you try to transpose this, you're going to get A plus E, B plus F, C plus G, and D plus H. And then you're going to transpose that, which is equal to A plus E, C plus G, B plus F, D plus H. So now if we were to transpose each of them, yeah, so okay, so all right. So A plus B all transposed is equal to A transpose plus B transpose. So this is going to be equal to A plus B plus A transpose plus B transpose And then you just do the rewriting. So we showed the first part of linear. Now we just need to know that that t of c times a is equal to c times t of a. So so we're gonna get like ca, or wait, let's call it xa, xb, xc, xd. And then you transpose that, it's the same. It's the same. So it's a linear transformation. Let B be any element of M2 by 2 such that it's equal to its transpose. Okay, so let B be symmetric. So B symmetric. So we're going to get like A, B, B, C. And we're trying to find A such that T of A is equal to B. So what we're going to get is A plus A transpose is equal to A, B, B, C. So if we instead just, wait. All right, let's let B equal 2A, 2B, 2B, and 2C, and then A is equal to A, B, B, C. Then if we do plus A, B, B, C is equal to 2A, 2B, 2B, 2C. So it's just some symmetric matrix that's like, I think it's B over 2, is it not? I'm pretty sure it's just B over 2. All right, show that the range of T is the set of B. Wait, hold on. Oh yeah. Yeah. No matter what you put in for A, you're gonna get a symmetric matrix out. But now it's a little bit different to say that everything you get is symmetric and you can get any symmetric matrix. But I think you can. All right, describe the kernel of T. So the kernel of T, so this is D. So ker of T is equal to the set of X such that Tx equals 0. So I think that the kernel is just 0. No, wait, hold on. That's not true. The kernel, if you have like A, wait. Okay. So it has to be zeros on the diagonal because there's no other way. And then if you have like B and minus B on the what do you call it? Is it called the anti-diagonal? What is that called? I always want to call it the anti-diagonal or something, but that's like sounds like a stupid name. Oh, it is called the anti-diagonal. Nice. Okay, yeah. So so basically, what you need to have is you need to have inverses on the corresponding anti-diagonal. So this is equal to the cur of t. All right. I just want to double check my answers on this one, but this one was really good. Dude, the both of these sections have been on chapter 4 have been really good. Yep, that's exactly what I did. And then you do this. Right, I didn't really do that, but yep, that's good. Yep. Okay, it's b over 2. Right. The pre-image of a symmetric B, right. I like that they're starting to use some of um these words that I like. Pre-image, I like that. It lets you know exactly what it is. The range of t. If b is equal to t of a equal to, then clearly nice. I'm gonna go get a jacket. I'm getting kind of cold, actually. All right, 46, 47, 48 are both really good, and then we'll end this section. Okay. Man, I've been talking so much. Okay. So we did 43, 44, and 45. All right. Alrighty then. All right, 46. Define t from the set of continuous functions on 0 to 1 to the set of continuous functions on 0 to 1 as follows. For f in C01, let t of f be the antiderivative f such that f0 is equal to 0. Show that t is a linear transformation and describe the kernel of t. Oh, what is the kernel of the integral? That's interesting. The integral of 0 is 0, right? Dude, what is going on with Firefox? Dude, Firefox is such garbage, man. Like, I don't know why I did that. Okay, yeah, the integral is 0, 0. That's what I thought. Because if you have the 0 function, then the area under that is going to stay 0. So that makes sense. So then the kernel, meaning the set of functions. Okay, so first we need to show antiderivative This is so cool. I love stuff like that. I don't know how to prove it though, but I know it's true. I just don't know how to prove it. So T's linear transformation describe the kernel of so the kernel is just the cur of T is equal to F is equal to little f of x equal to 0. So I think the kernel is 0, but I don't know the linearity thing here. Okay, it's equal to f of x equal to the integral of 0 to x. Right, okay. Is equal to the integral from 0 to x of f of t dt. All right, hold on. I'll be right back. Okay. So I don't know. I mean, I guess you just sort of use the additivity of the integral, and same with the homogeneity. Okay, cool. All right, and then it's just 0. Cool. Okay, 47. Let V and W be vector spaces, and T from V to W be a linear transformation. Given a subspace U of V, let T of U denote the set of all images of the form Tx, where X is in U. Show that Tu is a subspace of W. um, um, I think it's obvious because you can take linear combinations of elements of let me try to figure this out. So we have T from V to W, U contained in V is subspace. Then we want to know that T of U is subspace of TW, or of W. Okay, so let's say that we have TU and TX. We want to show that it's a subspace. So we're trying to show that this is in. Wait. Let's say let's say for x1, x2 in U, tx1 is in U. Let's call this W prime or something. W prime. Tx2 is in W prime because by definition. Then since x1 plus x2 is in U by subspace definition, then T of x1 plus x2 is in U, W prime. And then we just need to show that we can scale the elements. So we need to just show that C times Tx1 is in W prime. And the way that we do that is equal to, by the definition of it being a linear transformation, we have T times C of X, and C of X is in U by subspace definition. All right. So therefore, and 0 in U by definition. So okay. Okay. So then zero's in it. So okay, so we proved it's a subspace. Now we just need to do 48. And 48 seems harder. So T is a map from V to W as before. But given a subspace Z of W, okay, given Z subspace W, let U be X such that TX is in Z. Show U subspace V. Okay, so what we want to show is that so we need to show 1, 0 is in U. So okay, so since T of 0 is equal to 0, and U is defined as the set of X as the T of X is in Z, and 0 is in Z, then 0 is in U. Okay, the second thing is now we need to show for A, B in U, A plus B is in U. So take so T of A and T of B are in Z. Then T of A and T of A plus T of B is equal to T of A plus B. Therefore, A plus B is an element of U. And then finally, C times T of A is equal to T times C of A implies CA in U. Okay, so I just showed it. It's actually really easy. So you just sort of apply the definitions. It's not all that complicated. All right, so that concludes section 4.2. This is a good one.